This is Gold Standard Maths. I'm David Forster. In this lesson, I'm going to cover implicit equations, which is part of the differentiation or calculus section of the A-level syllabus. The differentiation involved here can be tricky, and these exam questions will give you an idea what to expect in the examination. So first of all, a fairly straightforward question. A curve is given by the equation x cubed add 3y squared equals 11. By using implicit differentiation, find dy dx in terms of x and y. So these questions, x and y usually mixed up. The equation is not written in the form y equals fx. Implicit differentiation means we just go through and differentiate everything with respect to x, and therefore the answer will not just be in terms of x, but x and y. So for x cubed, we differentiate to get 3x squared. For 3y squared, if we differentiate with respect to y, we get 6y, but we have to multiply that by dy dx. So it's been done in terms of x. This is another form of the chain rule, and 11 differentiates to 0. So we rearrange this to make dy dx the subject. 6y dy dx equals minus 3x squared. So dy dx equals minus x squared over 2y. The next question is similar. We have to use the product rule. So find the equation of the tangent to the curve x squared add 5y ln x minus x y squared equals 0. So implicit differentiation again. We're differentiating everything with respect to x. So x squared differentiates to 2x. 5y ln x, we're going to use the product rule. So for the 5y, that differentiates to 5 dy dx. ln x stays as it is. Then the 5y stays as it is, and we differentiate ln x to get 1 over x. For the minus xy squared, once again, product rule. Differentiate the x, we get 1 times y squared. Differentiate the y squared, we get x times 2y dy dx. And on the right hand side, 0 differentiates to 0. So we take all the dy dx terms to the left and everything else to the right hand side, and I get this expression for dy dx. In this question we want the tangent to the curve at the point 1 minus 1, so I substitute in x is 1 and y is minus 1 into the formula for dy dx to get the gradient 2. So I want the line with gradient 2 and through the point 1 minus 1, which is y equals 2x take 3. Another question to find the equation of the tangent. This time the curve is y cubed minus 3 cos x equals 8y e to the x, and the point is 0, 3. So once again we differentiate everything with respect to x. Y cubed will give 3y squared, but t times dy dx. Minus 3 cos x will give 3 sin x. On the right hand side we have to use the product rule. We get 8 dy dx e to the x plus 8y times e to the x. Now I could rearrange this to find dy dx as I did in the previous question, but in fact we don't need to do that. We need to find the value of dy dx when x is 0 and y is 3, and we can do that by substituting in those values and then rearranging to find the gradient at the particular point, which is 24 over 19. So I want the equation of the line with gradient 24 over 19 and through the point 0, 3, which is this here, and it needs to be in the required form, which is 24x, take 19y, add 57 equals 0. Do remember to put it into the correct form. We need a, b and c to be particular integers. Find the coordinates of the stationary point of the curve with this equation. So we're going to find dy dx, and this time put dy dx equals 0. So differentiating the left-hand side using the chain rule, we get 2 times x plus y minus 2 times 1 plus dy dx, which is what the expression in brackets differentiates to. On the right, e to the y differentiates to e to the y times dy dx. Now, I could rearrange to find dy dx, but I don't need to. I can substitute in dy dx is 0, and that gives me 2 times x plus y take 2 equals 0, y equals 2 take x. So if I substitute that back in to the original expression and solve, that gives me x is 2 and y is going to be 2 take 2, which is 0. So the stationary point is at 2, 0. So no need to find the general formula for dy dx here. The danger is you will rearrange and get it wrong. It's easier to substitute in the value of 0. The next question. A curve C has this given equation where a is a constant. We're told the curve passes through root 3 pi over 6, and the first part is to find a. In fact, to show that a is 2. It's a show that question, so make sure you really show the substituting in. I've written down the value of sine of pi over 6 and cos pi over 6 and rearranged to get 2. In this question for part B, we do need to show that dy dx is what is stated. So we do need a general formula. So differentiating with respect to x, using the product rule first of all, we get 3x squared sine y. Add x cubed times cos y dy dx. For cos y we get minus sine y times dy dx. And on the right hand side we get 2. So take all the dy dx terms together and all the other terms to the other side, and we get the expression as stated. Hence find the gradient of the curve at P. Now the point P was root 3 pi over 6, so we take root 3 pi over 6 and substitute it in to the formula for dy dx, and we get minus 5/8. The tangent at P intersects the x-axis at Q, so the tangent will have gradient minus 5/8, and it goes through root 3 pi over 6. So here's the equation, unsimplified. I put in y as 0, and I need to find x. So putting in y as 0 and rearranging will give me the exact value asked for, which is root 3 add 4/15 pi. Next question. The equation of a curve is given. It intersects the positive x-axis at P, and we need to find the gradient of the curve at P to be minus 3/2. So, I've first of all differentiated with respect to x to get 2 times x plus y times 1 plus dy dx, and on the right 4 dy dx plus 2. When the curve intersects the positive x-axis, y will be 0, and solving that we get x is minus 2 or 4. It's the positive x-axis, so x is 4. It's 4, 0 we're dealing with. So put those values in to the equation involving dy dx, and rearrange. We get the gradient is minus 6/4 minus 3/2 as required. Part B, find the equation of the normal to the curve at P. giving the answer in the form ax plus by plus c. So this time it's the normal we want. So a straight line going through the point P, and the gradient is going to be the minus reciprocal of the tangent, so 2/3. So the normal will be y take 0 equals 2/3 x take 4. In the form required, 3y equals 2x take 8. 2x take 3y equals 8. The next question, we have unknown parameters, p and q, unknown constants, and we're asked to show what dy dx is involving p and q. So differentiate everything with respect to x, so that's 3px squared. Use the product rule for qxy, so qx dy dx plus qy. And for 3y squared, that differentiates to 6y dy dx, and 26 differentiates to 0. All the dy dx terms to the left and factorise, all the other terms to the right hand and factorise, and divide to get the form required, where a is minus 3, b is minus 1, and c is 6. We are now given some information that will enable us to find p and q. We're given the point P, minus 1, minus 4 is on the curve, and the normal has equation 19x plus 26y add 1, 2, 3 equals 0. So first of all, I'm going to substitute in the point P, minus 1, minus 4, and that gives me one equation in P and Q. Minus P add 4Q equals minus 22. Now we know that the gradient of the normal will be minus 19 over 26. So the tangent at the point P will be the minus reciprocal, which is 26 over 19. So in other words, 26 over 19 is the formula for the gradient with minus 1, minus 4 substituted in. Rearrange that, we get a second equation, and then all we have to do is to solve the two equations to get P is 2 and Q is minus 5 as our required answer. Last question here. A curve has equation x squared y squared plus xy to the 4 equals 12. First of all, prove the curve does not intersect the coordinate axes. So if I substitute in x is 0, I get 0 plus 0 is 12. That never happens. Substitute in y is 0, we get 0 plus 0 equals 12, which once again never happens. So no intersection of the coordinate axes. Now we need to find for part B the general formula for dy dx. So we differentiate everything with respect to x using the product rules. So x squared times 2y dy dx, add 2x times y squared, 1 times y to the 4, add x times 4y cubed dy dx, equals 0. Take all the dy dx terms to the left and the other terms to the right, and we get this expression. Since y cannot be 0 by part A, we can divide by y to give the required expression. Part 2. Prove the curve has no stationary points. So we're going to put dy dx equal to 0, and since that is a fraction, it's the numerator that must equal 0. So we get 2xy add y cubed equals 0. Take y out of brackets, and we know that y is 0 is not possible by part A. So we get y squared equals minus 2. And putting that back into the equation of the curve and solving, and that's giving me x is the cube root of 6, which seems plausible, and y squared therefore equals minus 2, which is minus 2 cube root of 6. Y squared cannot be negative, so we discard it. There are no stationary points. The last part. In the case when x is bigger than 0, find the equation of the tangent to the curve when y is 1. Now, if y is 1, I put that into the equation of the curve to find x. That gives me x is 3 or minus 4. We're dealing with a case when x is positive, so it's the point 3, 1. Substitute that into the formula for dy dx. I get minus 7/30. So I want the equation with gradient minus 7/30 and going through the point 3, 1. And that is y equals minus 7/30 x plus 17 over 10. In this equation, they've not asked for any particular form, so that form will do. Just make sure you don't leave out the y equals when you write down the formula of equations. That is a reasonably common mistake made by candidates and will not be helpful.